So we're able to control the thickness of the panel frames using multiple attractor points. Now we're going to use an attractor curve, and we will be drawing this curve inside of Rhino. And the whole point of what we're trying to do is find, so let's draw this curve, just something real simple. And what we're trying to do is get the distance. So remember, I'm going to turn this off and turn on our area and hide our points. Essentially what we did was find the proximity of all these points to the multiple individual attractor points. What we're going to do is try to find the proximity of these points to the curve. And the easiest way to do that is to, let's instantiate our curve in Grasshopper. So we have a curve, set one curve, and then there's a node called closest curve. Curve closest point. So that takes in a curve and then a point. So we're going to feed in our points, which is this point in here. And so it's giving us the closest point of each of these points on the line. And so it's showing us what that point is. We don't know what it is, but if we draw a line to see the relationship, we have a list of points here and a list of points here. So you see, we can see the relationship between, it's saying the closest, this is the closest point to these 2 points on this curve. And we can see that as we start to modify, we see this change. And so just like we had before, all we need is the distance, and this gives us a list of distances, which is the length of these lines. What we want to do is just pass this distance, remember, into what we already had. So I'm going to pass this distance to get the bounds of that list of distances and pass that into here. And then now I'm going to hide our points, hide these points, and show this. Now see how this all of a sudden responds. So as I start to modify, we can see that the curve is controlling, because we've established the same distance relationship between this driver curve and the points that define the panel frame. But for us to understand the power of lists, what if we make this curve parametric so that it's not just a Rhino curve? And that's what we're going to do now. Let's clean up our file. I'm going to delete these initial points. We don't need our points anymore because we're going to be defining these with curves. Alright, so all we want to do now is this curve. Instead of having it Rhino geometry, we want this to be Grasshopper geometry. Okay, so what we want to do is set some constraints. Let's do this, hide this. We want our curve, I'm going to delete this. We want our curve, I'm going to also show not to exceed the boundaries of our points. For clarity, this is what the boundary of the points look like. So we put a bounding box just to get the boundary. This is per object, but we want it to be a union. So this is essentially, we want our curves to be within this region. Okay, I'm gonna delete that. The other thing is we want this to be the point that we use to define the line geometry. So essentially, we're going to be moving these points in such a way that their movement in the direction control the curve. For example, if these are points, we're going to move them up. Maybe this moves up. We're going to use them to create a new curve. Delete that. Now we have to sort the panel frame centroids by their Z component. So every centroid, which is a point, has an XYZ. We want to get the component so that we can, the Z component. So we deconstruct a point, feed that into here, and now we get a list of values that define the Z, a list of Z values that define these centroids. What we want to do is sort our centroid using this list of values. So when we pass this list of values into here, it creates a new list of values that goes from lowest to highest. But what it has done is it has created a new list with new indexes that do not align with the indexes here. Currently the indexes here align with the indexes here. But because it's done a sort transformation on this list, you have a new address for the items in this list. So the way to make our centroid correspond to this list is to pass the centroid as a value here. So it uses the key to sort the value. And so we have a list. Notice that this and this are very different. In fact, to visualize the difference, let's do a list item. Connect that here. Do another list item, so just copy paste and connect the original list here. But we want these to have the same index address, so let's do a value list of 0 to 20. So you see that when we highlight these two, they're not in the same position. Okay, and that's because of this sort transformation. In fact, as we move this slider, you will see they're vastly changed. Now we have our new points sorted along the Z. What we're going to do is split this list using the horizontal count here that we use to define the number of panels that we want in this direction. Okay, so remember, as we increase this, the number changes. So we want to split our list by that number, because that's how we get the first all the items the first whatever number of counts in this list. So what we do is we do a split list, and the list we want to split is the value, and it requires a splitting index. So at what index, so just like we have a list, at what index do we want to split this list? So we want to split it at an index that matches the horizontal count. So notice that we have, if we hover here, we have 77 values, but now we have 11 values here and we have 66 values. So what it has done is we have two lists. Oops. Coming out of here. The first list, delete that, and do a point to see what's coming out from here, is all of the points, because we sorted and we divided at 11, okay, but 11 starting from 0. So at the end of 10, which is here, we pretty much divided the list, and that's what we have. All of this is what's here, and the rest of this is here. Okay, delete that. So I'm going to move this over here as we build our code. This goes here, and these are the points that we need. I'm going to hide these, I'm going to hide these, I'm going to hide our point. So all we care about are these points. Okay, but if these points are going to be of any use to us, they have to be in order. Remember, we're trying to use these points. As we move them up, they create new points. We're trying to use these new points to generate a curve. So it goes from here to here and here to here. So that's how we create the new curve. But if they're not in order here, it might go from here to here and from here to here, and this is not the curve we want. We want this curve. So we have to make sure that these points are in order. To do that, all we have to do is sort points. You can notice from the icon, it sorts points in the X direction first, then in the Y, and then in the Z. Okay, so we're going to pass our points here. And when we do items, you notice that these points 1, 10, you start to see that these points, so you look here, are now in order. Okay, delete that. The next thing we want to do is, how do we move them in the Z direction in a way that is controlled? And the way to do that is to use a graph mapper. So I'm going to use a graph mapper, see it here, and you will notice that this looks like the MD slider that we used. MD slider that we used to define a point. But in this case, a graph mapper is more than an MD slider, even though there's some similarities. So let's say we can create a line in this thing. We can create a curve. But you're wondering, how does this actually work? So remember, you see these values we have here, 0, 1, and 0, 1. What this is telling us is, think of this like it says a graph. Okay? Now a graph has a y-axis and x-axis, and that's the origin. What this is telling us is this graph is going from 0 to 1 and from 0 to 1. Okay? And we have a curve right now that is doing this. How the graph mapper works is it takes in values, and the values it takes in define the x. So change the color here. It takes in values that are within the domain of the x-axis. So in this case, by default, the domain is 0 to 1. So 0 to 1 and 0 to 1. So it takes in values that are between 0 to 1, and it will match. Let's use this. Oops. It will find the intersection of these values on the curve. So this is an intersection, an intersection, an intersection, an intersection. So it projects these points along this axis in the y direction until it intersects. Okay, and then when it intersects, it pretty much will give you the z. So think of this as x, 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 x. And so the values along the 0, 1 y domain is what comes out from here. So as I begin to change this graph, it changes the value that comes out from here. But the interesting thing is your domain doesn't have to be from 0 to 1. With a graph mapper, you can set your domain. So x0 is 0 and x1 is 1. So if we want the domain to be from 0 to 10, we can do 0 to 10, hit OK. Alright. And so what this is doing is it's making this 0 to 10. And so our values that we feed in here, we need to make sure they're from 0 to 10. And wherever they intersect, they will give us, wherever these values intersect this curve, they will give us a list of values that are between 0 and 1. So think of this as remapping, but using geometry to remap values. It's remapping the values here using the curve to give us values here. Okay? Let's move this to the side. Might be useful to us again. Just gonna move this down here. Maybe just delete it. Question is, how do we get this? Let's move it back to 1. I like to keep everything related to graph map as 0 to 1, and then I can operate on a list of values from 0 to 1 using some other mechanism. But we keep our graph 0 to 1 in order to get the values that go in here, let's find the total length or range between 0 and 1. So we want a range. So the default domain, we want to construct one. Construct domain. Okay. And we want to be 0. I'll reduce this, and 1. Okay. All goes in here. So we have a domain from 0 to 1. But how many steps? We want it number of steps to be the length of the number of points that we have here. So we're going to push that in. As you notice, we have 11 points, and we push that here. Let me do a panel. Now we have from 0 to 1, we have 12, because this goes from 0 to 11. And the reason it's doing that is it's starting from 0, but it's going 11 steps. So it's going to go from 0 to 1 is 1 step, from 1 to 2 is another step, all the way to 11. But we want this to have 11 values between from 0 to 1, not 12 values. So what we're going to do here is under expressions, going to do x minus 1. Okay. Now what this has done is it has created the length that was 11 is now going to be 10, and so it's going to give us each step 10, but we have a total each step until it gets to 10 instead of 11, and we're going to pass that number into here. Okay, and you notice it's divided it into that. And the next thing that comes out from here is a list of values. Remember, like we drew, this is 0.1, this is 0.2, 0.3, 0.4, 0.5, that's why it's in the middle, all the way to 1. So 0 to 1. But then it gives us the corresponding values on this axis, and that's what this number is. Okay, so we have used a graph to remap a list of numbers. Move this here. Okay, now we're going to the list of numbers here. Okay, we're going to remap it. We're going to remap it so that it fits, remember, our boundary, right? Our boundary of points. We want to be able to move this curve within this boundary. So we want to move this point. The maximum should be from here to here. So we want to get the distance between this row and that row, because that's the boundary for our curve. So what we're going to do is do a construct domain, or actually all we need to do is bounds. Okay, bounds, which takes in a list of numbers like we did and gives us the domain, and what we want to pass in here is the z, because that will give us the lowest to the highest. Okay, see how these things keep coming up? That's why remap is essential to understand. Domains are essential to understand. So what what we want to do is remap these numbers using this target domain. So remap, to put this here, these values, the source by default is 0 to 1, which is fine because we have our domain 0 to 1, but the target, we put this here. And now we have remapped these values to fit within this domain, or this domain. Alright, so we have a new list of values that represent the move relative to this curve. So if we move our points, okay, we're going to move these points, or these sorted points, okay, in the z direction. Remember, when the x, this is x and this is z plane, and we're going to move it by a factor. Let's move this back by a factor of this. I'm going to hide my centroid and also hide, actually we can keep them. Okay, so notice that as we adjust this, these points are adjusting. Quite interesting. Okay, we can do different things with this. We can also change the mapper. See, able to now use the graph mapper to modify a list of points. It doesn't even have to be points. You can use the graph mapper to modify values that are coming in, but you're using geometry. Like now we're using a line. There's so many types. We can use a parabola. Move this up. We can use so many other types, so I will leave you to explore on your own. In this case, we're going to use just I'm going to use this option. Okay, this gives us a bit more complexity with the line, or with the points that will define the line. Okay, and it's so easy at this point for me to do an interpolate. That's interpolate, that takes in a point of vertices. I'm going to put that here. When I hide my point, I can move my line with the graph mapper. Okay, but notice that when I move it to the end, and when I move it here, it's supposed to be at 0 and 0 in the y, which in our case in the z, which is supposed to start from here. But why is it doing that? Well, it's doing that because notice that the bound that we have here is 4.7. So instead of it to start from 0, it's starting from 4.7. So what we want to make sure, and when we move this to the highest, you notice that it's going away from, here's our list of, it's exceeding our boundary. So we want to bring this down by 4.7 and bring this down as well by 4.7. So what we do is we deconstruct domain, deconstruct domain. Okay. And then we subtract. So subtract this value, which is the highest, from this value, which is the lowest, and then we construct domain which by default starts at 0, but now it's going to end here. So we move this back just so you see what's happening here. We have a new domain that's from 0 to 57, and because we subtracted these two values from this value, because that's the constant change in height, I'm going to move this here. Now you see that it's starting from here, and when I move this to the maximum point, it's here. So this is the line that we want to use to control our geometry. So I'm going to remove these, remove this, make our script a bit cleaner. Okay, we have our move, a new line. Now we can pass this curve into replace that curve. Okay, so what we do is just drag that, drag into here, and delete that. Maybe move all of this. And now when we turn on curve, we see that there is, let's hide this point. Now we can change this and see how it changes. We hide points again. We can modify this and continue to increase the fall off that we did for more controls. Okay, so now we're using a curve. Again, change this to a line. Okay, this is powerful for manipulating your facade or any other thing. That's how you use an attractor curve that's created parametrically using the graph mapper.